My name is Ben Sigelman. I am the CEO and one of the co-founders at Lightstep. I'm here to talk about observability. I think a lot of people here are already familiar with the term. I'm a little bit bitter about how many letters there are. It's just a lot of typing, but we have to live with it. But I'm here to talk about observability. I think there's a lot of discussion around both what that term means and how we establish an effective practice around observability. I spent my early days at Google working on what now sounds a lot like observability. I built out the Dapper tracing system there and then built Monarch, which is their high availability time series monitoring system. And at Lightstep, we work on similar sorts of problems. This is very much not intended to be a product pitch for Lightstep, but is more intended as a thought piece and somewhat provocative way to reconsider how we consider our own observability practice as an industry. So let's get started with the critique, which is the first section of this talk. All right, so this is the conventional wisdom, approximately, that we all know observing microservices is difficult. I don't think that's going to be controversial for anybody who's deployed them. There's a sense that Google and Facebook solved this. I mean, you can replace Google and Facebook with Netflix and Twitter or whatever, it doesn't matter. But there's this idea that this problem has been solved and that they use metrics logging and distributed tracing. So we should too. I think that's the essence of the argument, which doesn't hold water in my mind. It's not based on a first principles understanding. It also runs afoul of one of my biggest complaints about this type of argument, which is, as someone who worked at Google for a long time, we should not be emulating what they did. At least we shouldn't do it blindly. They often were dealing with scaling issues that we don't have to deal with outside of Google. They're processing 5 billion RPCs per second. It's a lot of RPCs per second. So if you're going to build a system that can observe 5 billion RPCs per second, there's a natural tension between scale and feature set. And you will necessarily give up features in order to scale with that sort of volume. And so the solutions that we can use outside of Google and Facebook are actually oftentimes a lot more powerful from a feature standpoint than what we could use at Google, because we don't have to scale to that order of magnitude. So this conventional wisdom, in my mind, is totally busted. It feels a little bit dogmatic to me at times as well. It is often represented as the 3 pillars of observability, and there are numerous blog posts and marketing posts and so on and so forth about establishing a practice of observability where we follow the 3 pillars, get something in place for each of metrics, logging, and tracing, and then voila, we're supposed to be done. So this is what metrics look like. These are a bunch of squiggly lines. I'm not here to lecture anyone about what these are. I think people are familiar, but you have statistics, you sample them frequently, and then you draw lines between the samples. Logging is also something I think we have a firm understanding of. Of course, you can do more fanciful things with it, but at the very lowest level, you have statements in code that you write or link. They emit structured or unstructured data to a log file, which is then centralized, and then you can search over those log files to generate a list of logs and get some primitive statistics back as well, or in some cases more sophisticated statistics, but this is logging. I think people are probably familiar with that too. And tracing usually looks something like this in people's minds. This is a screenshot of Zipkin. There are many other tracing systems that have a visualization of a distributed trace. The common elements are a shared timeline, the fact that the segments of the trace come from different parts of a distributed system, and that you can understand what caused what, which allows you to essentially understand the critical path of the trace. So kind of quick show of hands, the metrics, logging, and tracing slides. People familiar with these concepts? Yeah, great. Okay, cool. So we're aligned about that. All right. So I think when we think of things, it's nice to think of them in 3s. I've thought a lot about why this 3 pillars idea has caught on so much. I think part of it is that we like threes a lot as human beings. These are three sets of three things that I really like. I tried Rice Krispies again for the first time in honor of this slide. I hadn't had them in decades. They're very good. Really good. And it's not just the threes, they're just delicious. But I think part of it as well, more seriously, is that we as users of tools have been frustrated by people that are promising things in terms of use cases and value propositions, and we want them to be more factual. Do you or don't you support metrics? Do you or don't you support tracing? Do you or don't you support logging? And these are things that we can assess objectively and use to grade observability solutions. And that does have some appeal. But they all have fatal flaws. This is one of my favorite cartoons in the last year. We need to be vulnerable. I think that it's difficult. One thing I will say in favor of what it was like to work at Google was that there wasn't, no one is trying to sell anything to anyone else at Google. So you would willingly represent your flaws as a service. You'd build something and say, well, this is what's good about it. This is what's not good about it. It's very hard, especially at conferences like this, to get people who build systems to get up on stage and talk about what doesn't work about their system. But we need to do that. It's nothing to feel ashamed of. Every system has a trade-off. And that's one of the biggest, if I could get one thing like propagated into this whole conference, it would be that we should all come up here and present what doesn't work as well as what does work. But we need to talk about those too. And these are still understood, but maybe not as clearly as understood as what these things look like. So first we'll start with metrics, and a word that no one knew in 2015, or not very many people knew anyway. So we have tags. They're useful to explain variance. So here's a time series. This is a real example from one of Lightstep's internal systems. Anyone that's looking at this can see that there's some kind of anomaly that happened around 1 p.m. The obvious question is what happened. So you have a tag on that, you group by that tag, and you get a new set of lines where you can now see that this anomaly came from one particular value for that tag, which is not a root cause, but is a useful piece of information. We now know that that tag value is probably highly correlated with the problem, and so we have a lead that we can go on. So this is really useful. The issue is that the number of values for the tag is expensive, and that's called cardinality. So the cardinality of a metric is the number of values for a tag. It was previously something that we learned about in our college set theory classes and then forgot the word, and now we're all relearning it again. But this cardinality issue is ironically like part of product marketing for a lot of companies now because it's such a significant pain point for metrics. I'm assuming people are familiar with this idea if they're at this talk. Logging also has a fatal flaw, which is basically just the cost of the data itself. I mean, we were already spending a lot on logging, whether it was Splunk or Elastic clusters or whatever, when we were just dealing with a monolith where you had, some constant number of logging statements per transaction. You're now seeing a transaction that is, if these different boxes are services, you have regular transactions are traversing many service boundaries. So if you want to use logging to understand these transactions, you have to log about each entry and probably exit point from those services. So you're multiplying the transaction rate, which is a function of your business, which you don't really that's okay. As your transaction rate grows, you can spend more money on things, but you're now multiplying it by every microservice. So if you build out a microservice stack and you go to 10 to 100 to potentially thousands of microservices at a large organization, your logging cost is scaling roughly linearly with the number of services. And that's a big problem because your value is not scaling by orders of magnitude. So the logging data volume, when you include the cost of the networking and storage for this data and weeks of retention, ends up basically just being way too much money. I was at a talk, I was at a conference last year and someone was I won't say who, I didn't ask them for permission, but he was presenting about his company's logging infrastructure at a monitoring conference. And this company is, like, in my mind, a real honest-to-goodness thought leader in this space, and they're doing lots of talks here today and stuff like that. And I asked him, what's the summary of your talks? I couldn't attend your talk about logging and microservices. And he said, oh, it's very simple. Don't do it. And that was the moral of the story. And we had the same problem at Google. And the reason we started Dapper at Google was specifically because this is way, way, way too expensive. So we solved this with Dapper by sampling. So we wouldn't sample blindly. We would sample an entire transaction at a time, but we would retain very few of them. So we had this equation, same equation here. What we would do is say, not for every logging statement, but for the entire transaction, we will either keep or discard the transaction. And by only keeping 1 in 1,000 of them, we were able to significantly reduce the cost of getting this data out of the process and into regional storage. I thought that would be enough. It turned out it wasn't. We had to do another 10x decimation of the data to get it into truly global centralized storage. So when it was all said and done, we had 1 out of 10,000 transactions restored. The other 9,999 were discarded without consideration. So the sampling was completely blind, and there's no other way for us to have accomplished that. And so this is a major problem, because if you're dealing with an outlier, by definition, it doesn't happen very often, and you probably lost it. Similarly, if you want to do some kind of aggregate analysis focused on a particular aspect of your system, you probably don't have enough data to use to accomplish that. Dapper gets some credit for doing some great things for Google. It was really useful for web search, for ad serving, things like that, where we had super, super high throughput. But for low throughput products like Google Checkout or even Google Spreadsheets, it was of limited value. It did have some value. It wasn't useless, but it had a lot of problems because we threw out so much of the data. We couldn't make meaningful statistical statements about these systems. So those are the 3 fatal flaws. I mean, this is a table kind of reviewing them for people. It's impossible to find a solution that's just vanilla logs, vanilla metrics, vanilla traces that scales gracefully, accounts for all the data, and is immune to cardinality issues. Does this resonate with people, or is anyone upset with me? Okay. Well, anyway, so this is my critique of the 3 pillars. So I've talked to a lot of companies as part of my job who've deployed the 3 pillars, and then they're still in a world of pain. And this is basically why, is that you can deploy them, and that's not enough. You have to think about something a little bit deeper, and we need to be smarter as an industry about how we evaluate observability. It's not just these 3 checkboxes. All right, so yeah, no silver bullet. I think bullets are scary. I put this slide in just before the talk. I regret it, especially when they're that big. But yeah, there's no silver bullet. There's this other problem, which is that data and UI. So if you search for computers, here's computer, and what we get back are pictures of monitors. It's the same issue with these 3 technologies. Metrics, logs, and traces, those are the screenshots I showed earlier. It's a bit of a misnomer. I mean, you can use logging data and tracing data to generate time series. You can represent, the traces are really just a specialized form of logging, so you can represent them that way. There's all sorts of other visualizations that have nothing to do with these 3 things that we always think of in our heads that come from this raw data source. And another thing we need to understand is that these 3 technologies are important, and I'm not saying they're not good, by the way. I'm just saying that they're not the right way to think about things, but they're just data. Metrics, logs, and tracing are just data. They're not a feature. They're not a use case. They're just data. So again, we can collect all of them, but if we don't do something with it and we're not intelligent about the way we consume the data, it's not that useful. So this is my segue to talk about the second half of my talk, which is the scorecard for observability. So I basically, I've thought a lot about this, and I'm trying to get something up here that's not a bunch of checkboxes, but also isn't something that empty product marketing can satisfy, something that we can actually look at to evaluate observability. I'm going to write a much longer form version of this as a blog post in the next couple of weeks, which I'll publish. And I don't know if anyone's going to read it, but it'll go into more detail than I have time for in the remaining 15 minutes of this talk. But I would love critiques from anyone in this audience if you want to reach out to me separately or after the talk, because I'm still refining these ideas. But these are basically the 2 goals. We should think about goals and activities. So to me, goals are really, if we're talking about an individual service, our goals are related to how our services perform in the eyes of their consumers. So everything in my mind takes a service-centric view if you're talking about a DevOps kind of world. And then we should also think about the activities that we take as operators to accomplish those goals or to further those goals. So I divide observability into these 2 pieces. In order to make sense of this, we have to talk about SLIs. If people are familiar with the Google SRE book, they talk about SLI, SLO, SLA. It's basically, SLI is a service level indicator. It's an indicator of the health of a service that a service's consumers would care about. So that's to differentiate from something like for instance, if you had a Kafka queue, an SLI may be how long it takes a message to get into and out of that queue for a particular topic. That could be a good SLI for Kafka. You would not want to look at the CPU load or the number of nodes you're running as an SLI. Those are details of how Kafka is run. The key thing here is that most services only have a small number of SLIs that really matter and that really need to be measured, which is a good thing. So it's kind of like, if you can't explain which SLI you're going to move for a particular optimization you're making, you probably shouldn't be making it, or you're just guessing. So SLIs are, in my mind, the first step to properly running high-performance services. And there are two basic goals, getting back to the goals and activities. You either want to gradually improve an SLI. So this looks like, your PM is saying that your product is too slow. So you're going to spend a couple of quarters making a series of optimizations and refactoring services in order to make the SLI better as a baseline. And then the other version is that your SLI was like this for a while, and then suddenly it's way out of alignment, and you need to fix it as soon as you possibly can. This almost always takes the form of identifying something that you need to undo, like a data push or a new service release. It might be someone else's service, but these are very different things. And we talk about observability tooling without identifying which goal we're trying to move. So yeah, this one takes days, weeks, months. This one takes like, do it now. This is the one that wakes you up. They're both super important goals, but we should think about which tools we're using for which. And if you aren't thinking about that, you're probably you're more likely to choose the wrong tool. The two activities that we're pursuing while we're in service of those goals, in my mind, are detection and refinement. These, again, are things that we can reason about and discuss in isolation, which makes them effective ways to evaluate observability solutions. Detection is about reifying SLIs as specific numbers, so P99 or the throughput or the error ratio, those sorts of things. Refinement is about reducing the search space, and I'll talk more about that in a minute, but this is another thing where I think there's some false hopes around what we can expect from our tools, and I'll get to that in a minute. So for detection, I have to have a quick interlude about stats frequency. These are 4 graphs of exactly the same data from an internal system. The only difference is the smoothing interval that we use to compute these percentiles. So these are, I think, P99 of some signal. This is, I think, at 1 second granularity, 5 second, 10 second, 25 second. And it's not just that it gets smoother, which it does, but it actually goes down too, because as you smooth over longer intervals, you're not seeing some of the outliers. And there's a lot of interesting things you see. If you're able to get down to 1 second resolution or 5 second resolution, you'll be able to detect patterns of failure that you won't see if you smooth things out. In this bottom right graph, it's unclear to me whether or not there's a steady state regression or whether it's intermittent. If you look at this one, it's much more obvious that something intermittent is happening, which is the case in this particular incident. And that's actually an important clue. So I'm going to talk about the next slide, but I wanted a visual for it. So this is my scorecard for detection, if you buy my argument that observability is about detection and refinement. So for detection, we need to understand the cost of cardinality. I think there are a lot of people who make cardinality out to be something where we can't pay $1 for it. That's not true. You do need to pay for it. Just know how much you're paying for it. Understand that. Get it written down. Make sure you're thinking about it as you structure your metric strategy and inform your developers. And you also need to understand what stack elements you can actually measure. Can you go way up into mobile and web with the same solution that you're measuring your services? Because if you're trying to improve end user latency, you really ought to. Similarly, can you go below your application code into your open source dependencies and managed services to get a sense of how failures at that layer are propagating up into application layer issues? So specificity is about understanding cardinality and stack support. Fidelity is correct statistics. I'm putting escalation points here because it blows my mind how incorrect P99 is. A lot of solutions that people pay a lot of money for will take P99 across different hosts or different shards of a monitoring service and then average the P99s together, which statistically is meaningless, completely meaningless. But I swear it's commonplace. It's absolutely commonplace, and it's a difficult thing because you have to compute the P99 at the very end. So if you haven't been storing histograms or meaningful summaries, you can't really compute the P99 globally, which is what you actually wanted. So be careful about statistics. If you're measuring P99, that's smart, but make sure it's actually P99 because a lot of times it's not. You also want high stats frequency, which is that last slide. I think that for detection to work really well, you want to be able to detect the difference between intermittent and steady state failures. And that's only easy to do if you have high frequency data. And then of course, freshness, which is sort of obvious, but I have seen people design really cool observability solutions around, Spark and things like that. That's actually awesome if you're trying to analyze MapReduce jobs, but if you want to do real-time analysis of your system, just make sure that you're buying technology or using technology that will give you, hopefully less than 5 seconds of lag between what's happening in the world and what's on your screen. Okay, so pausing for refinement. So why refinement instead of something else? So my observation, this is of course completely scientific, this graph that doesn't have any units on it, but as you add microservices, the number of things your end users care about doesn't change. And so as engineers or as developers, we have to accept the fact that we have created a monster as microservices because our bosses or more importantly, our end users and customers don't care about microservices. Like they don't care that we're using microservices, but we've just introduced, I would say, a super linear number of failure modes as we add microservices. I think, I'm not going to try and quantify it, but certainly service-to-service interactions introduce all sorts of ways for things to break, and many of them are pretty elaborate and hard to predict. And so I think that just even if you could build a dashboard that had every possible failure mode on it, we don't have time as human beings to sort through that list. I've seen people building dashboards and even advertising dashboards that have this dizzying, just pages and pages of Spark lines and things like that. It is sort of impressive from just a consolidation standpoint that we can do that, but it's totally inactionable because if there's a failure in a microservices environment, it will crop up in many services concurrently. So you'll be dealing with many lines that are spiking at the same time, and you're left with this kind of guess and check linear search thing, which is really painful. So what I think the crux of observability is detection and then refinement of the search space. We're not going to find observability solutions that reliably tell us the answer and fix problems for us. If they do, I'm really scared because we'll all have to get different jobs. We'll be out of work. But thankfully, our job security is intact, I think. We're still going to need human beings to actually make decisions, but we can use tools to reduce the search space and to refine it down to a set of hypotheses that are actually credible. And so an observability solution is mainly about eliminating hypotheses before you investigate them. That should be the goal of refinement. So, right, must reduce the search space. So, yeah, we discover variance in our systems, usually initially through an SLI that's out of whack. We explain it using observability tools. That explanation is usually in the form of new variance, which we then have to explain again. And we keep on doing this until we find something that we can fix, either by adding caching or getting rid of serialization or rolling back a release. We're looking for variance that can be explained by a problem we actually know how to solve. And what I've seen a lot in organizations is that I've seen organizations, brand name companies that have really smart people who've been working really hard and care a lot about the outcome of the company, where they don't have good tools. Then they do have good tools because they, use something new. And suddenly they fix problems that improve SLIs by 50% or 70%. And they do this in the order of days just because I think people have lost confidence that they'll be able to find the problem. There's so many possible areas to look that they don't even feel like they're going to be able to enumerate the possible issues. And so they find huge wins once they have the right tooling because they aren't contending with this list of 100,000 possible problems. So I also want to talk a bit about histograms. I said this wasn't a product pitch and I mean it, I just don't know where else to get this. So this is a graph, histogram showing latency for a particular request. This is slowness, basically. The further right you go, the slower you go. The further up you go, the more data there is. So it's just a histogram. P99 in this diagram is right here. It is useful to know where P99 is for sure, but I think it's much more useful to understand the shape of a distribution. I'm kind of adamant that histograms are the right way to do refinement of latency because you can observe these sorts of multimodal behaviors very easily, and a human being can pick them out, select them, and reduce their analysis to the mode that they're concerned with. So I would encourage people to think beyond just percentile measurements to think instead about visualizing the entire distribution, whether it's a histogram or something else, so that you can find these different modalities and drill into them individually. The refinement scorecard is thus. Cardinality is, again, really important, arguably even more important than in detection, in that we need to understand how many dollars we're spending for more tag values. We do need, I think we still need metric solutions to be clear, but we should just be really careful about what we're going to pay for them with cardinality, because if you're using metrics to do the refinement process, cardinality is literally your only tool to accomplish that goal. So you have to be careful about that. Robust statistics, so that's histograms in my mind. There might be other ways to do it as well, but I think going beyond percentile measurements is pretty important for refinement. It certainly can help you, reduce this entire set of hypotheses, which this is a log scale thing, but we're only looking at the top 0.05% of requests here, and that's a nice thing to be able to refine and zero everything else. We also need to think about how long data is retained for. This is mainly, in my mind, in order to explain what's normal and abnormal. Another common practice in a microservice architecture for observability is that you find an issue, it looks bad, and you don't know if it's always been like this or if this is just normal. It happens to me all the time. And if you don't have a system that can show you exactly what you're looking at, 2 hours ago or a week ago, it's really hard to answer that what's normal question. And a lot of time series data is really just trying to answer that question. I would argue there are other ways to do it than showing a squiggly line, and I think we should actually explore those as an industry, but you need to understand what's normal. And again, I'll harp about this correct statistics. We have a lot of incorrect statistics out there, and that's dangerous. And then the last thing I'll say is about suppressing messengers. And what I mean by that, this is a diagram that's simplified, but if your service up here depends on an intermediary service, which depends on some tertiary service, and the tertiary service fails, you don't want to blame this intermediary service for that failure, but it will represent the failure in its own performance. And so you often have incidents where you'll be woken up or someone will be woken up because there are errors or latency down the stack. You shouldn't waste any time on the intermediary messengers of that failure. And an observability system that's able to understand the global picture should be able to suppress those hypotheses for you and refine that search to focus only on the service that's actually having a problem. And in turn, you can hopefully figure out what's causing load in that service and refine the hypotheses of where the load is coming from above it in the stack as well. So that's my scorecard for refinement. Okay, so how am I doing? Pretty good. So wrapping up, first to hint at my perspective. So here's a fun game to play. So design your own observability problem. So observability systems, you can have high throughput, high cardinality, a lengthy retention window, and a lack of sampling. So choose what you want. Actually, no, you can choose 3. Exactly 3 and no more. It's not possible to have all 4. No one's going to solve that for you. We're all trying to figure out how to get all 4 via approximations. And this is the essence of the problem. I see a lot of people advertising some really cool SHIT, but it's because it's not scaling, or they advertise something that's really compelling but would break if you had lots of tag values, etc. But this is the essence of the problem, and why there's still so much activity in this space is that no one has. This is a law of nature that we're dealing with. I call it observability whack-a-mole. So you can kind of move things around, but you're still going to have to deal with these problems somehow. I talked about Dapper earlier. I do think that tracing data is probably the best data source we have, in that it's the superset of logging data for transactions anyway, and it also understands context, which is super valuable for suppression of hypotheses. So tracing data has the raw material to suppress hypotheses about parts of the system that are reflecting failures but aren't actually the cause of failures. So I think tracing is really useful. This retention thing is just a killer, though. I think Other approaches retain 100% of the data for some period of time, and then we do fancy things about how we actually sample from that to explain hypotheses dynamically. This is, I think, a nice angle on this problem. There are certainly other approaches as well that don't do this, but I really like this approach. And here's my scorecard, in essence, just summarized down to one slide. But this is just, summarizing what we talked about already. So I tried to keep this to half an hour, and I did. It's 5 o'clock, and allegedly I have 35 minutes for this slot, so I wanted to leave time for questions. So with that, I thank everyone for attending my talk, and I'll open it up to questions, which I can repeat. Oh. Questions? Yes.
So if your dependent is then like writing some alarms without alarm what is the best approach to this? Does the observability system has to know the topology of your dependencies?
Yeah, so the question was, what do we do, how do we actually expect our observability system to detect these messenger systems and suppress issues with that? I don't know how to do that without tracing data being involved in some capacity, but I think I'd like to get to a world where we don't look at traces anymore. I think the tracing data is the fuel, not the car. The fact that we need traces doesn't mean we should be looking at them very carefully. So I think the idea is that you have enough tracing data that you can automatically understand that the critical path for the lion's share of your P99 requests are bottoming out in service X, way down the stack, and you just present that as the hypothesis to investigate. And you might even exonerate the services on the way and say, these are not your problem. These are not the droids you're looking for. Focus on service X. So that's how I think of it happening. So tracing data would be the raw data, but then the solution needs to use that. By the way, I should have said this earlier, but with all these suggestions in terms of how to measure stuff, my hope is that people can use a scorecard like this when they're evaluating open source or vendor solutions to think about their own systems and what workflows they have, map it to these things, and look at the shiny features and figure out whether or not they actually map to the detection and refinement processes for your organization, because each organization is different. If they do, that's wonderful. If they don't, then you should probably move on. But I think this would be a great thing to see people advertising, and then you can assess it with your own system. Other questions? Yes.
So so what is the average that you perform? There's many ways to do the 99%.
So the question is how to aggregate 99th percentile correctly? Yeah, so with some technology, I don't actually know how to do it because I think they've made some bad design decisions, but I think the best way to do it is to keep track of pretty fine-grained binned histograms or HDR histograms or something like that. Those things have an algebra where they're distributive and commutative, so you can take them globally, merge them up to the very top, and once you have one aggregate histogram with a lot of fidelity, you can take a P99 with a bounded error bar on it. So you can say this is guaranteed to be within 5% of the actual P99 if you kind of do the math out. But I think it's about maintaining histograms throughout your data processing pipeline. Yes? So let me make sure I get the question right. So how do you maintain statistical significance when you have to sample data? Something like that? Yeah. So if you're dealing with 1 in 1,000 sampling, how do you make statistically significant statements? I think it's necessary to rethink the way we do sampling. I think the aggregate ultimate sampling rate will be similar to that, but I think the sampling decisions have to be made after the fact. Maybe not days after the fact, but maybe seconds after the fact. And then you have enough information, even after a transaction is finished, to have a better hunch as to whether or not you need it or not. And so that's the approach I'd like to see taken in the industry in general. Certainly like my philosophy from Lightstep's perspective, but that's the basic strategy, because then you can bias your sampling towards the questions people are asking instead of making it just totally arbitrary. Any other questions? Okay, great. Well, I'll stay around after the talk. Thanks a lot, everyone. I hope you enjoyed it, and send me feedback.